All right, it is finally time to put everything together and talk about a matrix equation. So a matrix equation is if you have an m by n matrix with these column vectors, okay, and then B is in Rm, then this as an equation, if you think about what we talked about in the last video, Ax is really this equal to B. But we talked about this, again, this is going to be just the system of solutions, okay, where you can augment A with the B vector. And it has a solution if and only if B is a linear combination of the columns of A, because that linear combination piece, those multipliers, are your X vector. Okay, so everything we've talked about so far in this chapter is kind of coming together in this piece. So let's look at an example. Here's A, and here is B. Is the equation AX equals B consistent for all possible B1, B2, and B3? So remember, the only way we're going to get that this is inconsistent is if we end up getting zeros and then a number. Right, so that's what we are looking at here. So is there a linear combination for us in order to get a solution is what we're going to be looking at, okay? So we're going to look at the augmented matrix. And let's just write for our knowledge what that means. That means that x1 times this column vector plus x2 times this column vector plus x3 times this column vector must give me the solution B1, B2, B3. And there must be a unique solution for that linear combination if there is an x1, x2, and x3 in which this is true. Okay, in which x1 times 1, x2 times 3, x3 times 4 gives me whatever B1 is. And that's true for all three of those equation pieces. Okay. All right, so let's go ahead and do some work here on our rows. So if I take 4 times R1 and add that to R2 and put that back into R2, and 3 times R1 and add that to R3 and put that back into R3, I get 12 plus 2, 14, 16 minus 6, 10, and 4B1 plus B2. Because I don't really know what B1 and B2 are, so they're just going to stay like that. All right, 9 minus 2, 12 minus 7, and 3B1 plus B3. Now, if I take negative 2 row 3 and add that to row 2 and put it back into row 3, let's see what happens. All right, I end up getting 0, negative 10 plus 10, 0, and negative 2 times row 3 plus row 2. And that ends up giving us the situation we talked about for it being inconsistent, doesn't it? If you have all zeros in a number, there is no way in which this can happen. So is this equation consistent for all possible B1, B2, and B3? And the answer is no, it is not. It is not consistent for all of those. All right, here's another just set of definitions to close us out. So if A is an m by n matrix and the following statements are logically equivalent, okay, that is for A, they are either true or they are false. So for each B in Rm, the equation has a solution. So if that is true, then B must be a linear combination of the columns of A. Well, that makes sense because then there's an x1a1 plus xmam that is equal to B, and that's what makes it a linear combination. So that makes sense. The columns of A are a span of Rm. Also, that makes sense because B is in there. Okay, and A has a pivot position in every row. So what does that mean? That means that we end up having ones all on that diagonal. Okay, that you have a pivot position in every row. You don't have any free variables, if you will.